so delighted to see we have a really nice turnout for this discussion. And leading our discussion today is Gregory Falkovich, otherwise known as Grisha. And it was his idea, and a very good one, to have this discussion. And Dr. Falkovich is the Polak Professional Chair in Physics at the Weizmann Institute of Science. And he's also a regular visitor here at the center for many years. And he holds many workshops and programs. So we're delighted that he offered the suggestion. So just very briefly, we're going to have a discussion today. And so be candid, speak your mind. So it won't be lecture style, it'll be led by Grisha. And of course, it's about the movie Oppenheimer. And it's based on Prometheus, American Prometheus, the 2005 book by Kai Bird and Martin Sherman. And I won't go into the whole movie, but it has many complexities and fragments that tell the story of a man during one of the most important times in our scientific history, and being accused of communist boogeyman and things like that. But anyways, so let me turn it over to Grisha now as he leads our discussion. Thank you.
Thanks, Lorraine. And well, thanks to all of you for coming, and it's really hope will be a free-wheeling discussion. Thanks to Louis for making it possible. This is a physicist discussion in the sense that I'm a physicist, but you are welcome to bring different perspectives. And but it's historical, and what I learned when you are amateur historian, that what is your profession essentially is not the main personality, is the whole will be other people appearing in this picture. And so what I'll try to do, I'll try to let you see the other people. Of course, they will be about Oppenheimer, but also about other people. And also when physicists look at something, that first of all we see these people, and sometimes we also see an experimental curve or a simple formula. So I'll try to let you see this. And also we'll try to do it a little less Americano-centric than it may seem, because this is a part of very, very big picture, and we're still living in this picture. Okay? So as a physicist, as they say, physicists always start from first principles. So of course, any rabbi or priest will tell you that they really have first principles, but I'm not a rabbi, so I'll start from physicist first principle. And one of them is that we believe that what rules the world of physics as the world of phenomena is free energy. And free energy is essentially, if you look at here, it's energy minus entropy. And entropy is a lack of information. So to put it simply, if you let system be as it is, it goes down to the minimum of free energy. It's called thermal equilibrium. Or if you ask what it means for us, it means death. When you're in a thermal equilibrium with the environment, you're dead. Which means that we want to be not dead, so we need somehow get this free energy, and all this bunch of creatures trying to get free energy. And it consists of two parts, energy and information. So in a sense, if you are a physicist, you look at mankind as more or less struggling to get energy and information. And to a large extent, what I believe we are living now through this period where we're shifting focus from energy to information. We're still doing both. I mean, we need both for survival, but focus changes. And the people who will be in this story, those are people who were participating in the most energetic events that mankind knew, which is not a nuclear explosion, incidentally, it's thermonuclear explosion, and also started information age. So I really want to see you from this perspective, and it kind of opens somewhat new angles in it. So there's physicists watching, and this is a real historical picture. This is Oppenheimer, this is next director, this is Gregory Bright, this is Richard Feynman, this is Teller, this is Fermi. Kind of, I just want to see you the real faces. And of course, they aren't watching movie Oppenheimer. They look at the blackboard where Hans Bethe writing some formulas, and that's more or less the modus operandi in which, and I will return to this picture over and over, because this movie, what I like particularly about it, for me, who very much likes this epoch, many stills look like historical photos. And then they start moving, it's just unbelievable. But it all started, one may say, why? Actually, the people doing atomic project, and here we first see this energy and information coming together. It started from Szilard, Leo Szilard, who invented the idea of chain reaction long before this in 1934. Because he was a chemical engineer, and unbelievably, many of the people who did all this nuclear quantum physics and computer, etc., were chemical engineers, but their first profession. And I think it's important, because when I look at it as a physicist, and when I ask why these people did these great things, then you realize that they were getting into physics at the time when it was not a mass profession. When these Budapest people, Szilard, Wigner, and others, asked their fathers, I want to be a physicist, that Wigner's father asked him, how many are jobs for physicists in Hungary? And he said 3, and there were actually 2. But chemistry was a profession. There was already chemical engineer. All these people were chemical engineers, including von Neumann, who is a great mathematician. So Wigner got his, Szilard got his chemical engineering degree, and they started to do PhD in physics. And he got problem in Berlin University from Max von Laue, and he hated it. So in the corridor, 12 years before this, in 1926, this is 38, maybe, sorry, this is wrong. No, yeah, this is 38, that was 26. He met relatively young professor, Einstein, and so let me show you how they actually look like at this time. This is Szilard 26, this is Einstein, and told him that I don't want to do my PhD, what von Laue gave him. I have some other ideas. And after 5 minutes, Einstein said nonsense. And after 15 minutes, he said, OK, write it down. And in this conversation, the word beat was first spelled out. So Szilard, at least from the viewpoint of physicists, this is how information theory started. And Szilard was talking about Maxwell demon, etc. In 1934, being chemical engineer, walking on the street of London, it was like, I mean, Szilard described it very, very interesting. His memoir, he was just, and I know this corner in London. I just did like this, and then he was frozen, and then stepped back. At this point, he saw the idea of a nuclear chain reaction. It was not even about uranium. He thought about beryllium. That was long before Strassman and other things. And then, of course, in 1938, when all this news about uranium appeared, he went to Einstein, and they wrote this letter to Roosevelt, which has absolutely zero effect at the moment that it was sent. It took a lot of time and Pearl Harbor and many other things before American system started to move. But I wanted to show you this picture because then it is Szilard and Fermi who did the first reactor, and then we'll see why they did, and other people, yeah.
That was on Long Island, nowhere.
I don't know. It's somewhere near the fork. Really? Yeah. And Taylor was a driver because Szilard did not drive. So Taylor always says it's my historic. I mean, I will be known in history not as a creator of thermonuclear bomb, but as a driver of Szilard to Einstein on Long Island. Okay, so this all started on Long Island. Thanks.
There were 3 of them: Wigner, Szilard, and Taylor.
Yeah. Okay. Good. So now a movie really. I mean, this story that was before some kind of press story, but the story, real story, and it will set also the images which appear and reappear. This is 2 people. One is Oppenheimer, and it's Upper West Side. It's very important where these two people come from. And this is Lower East Side. This is Isidore Rabi. And it is a really important scene in the movie. And then in the movie, you see Rabi and Oppenheimer coming together and orange appearing. I never read anything, any comment of the author. Is this orange is really the same orange which is somehow resonate with orange from a Godfather? If you know the iconic orange in the movie Godfather, in the whole series, orange means death. And Coppola explained it how it actually came to be. They look for something which would be bright and spell like Italy, like home. And so it was this orange. And then in the first Godfather movie, it is he kind of almost touches the orange, and then he does not take it, and assassination, and he survives. And then in the next movies, every time somebody takes orange, he dies. This is from other scenes. Here, orange plays different roles, but later in the hearings, when this kangaroo trial happens to Oppenheimer, again, Rabi comes to him and again gives him orange. And the second time he takes it, and this time he does not. And of course, it's orange means something else here, and later I'll show you another movie. But this is really important scene because maybe I'll say a few words about Rabi, who appears in the movie over and over again. And because the movie is called Oppenheimer, not many people know that this other guy is Rabi. So I want you to know this other guy is Rabi, and indeed is much more important thing for the Second World War than Oppenheimer. He was in MIT Red Lab, and they did radar, which is much more important than nuclear weapon for Second World War. No surprise, he got his BC in chemical engineering, as all of them. But what also about Rabi, I live not far from this Rabi Street. We have actually crossing Oppenheimer Street, have Rabi Street and Feynman Street, not far from the Weizmann Institute where I work. You know where it is? Yeah. And, but interesting things about Rabi, and this is something which I think a recurring theme of this movie, is a question. So he always says that when he came back from school, his mother always asked him, did you ask a good question today? And that would make a scientist, and that I think we'll see later what kind of questions they ask and how it unexpectedly led to different direction. And I think that it's consciously that movie is made around one of such questions. So that's Isidore Rabi. And those are historical pictures. I just want you to see these people because this is Fermi, Lorentz, Rabi. This is von Neumann, Feynman, Ulam. They will all appear. And if you look at the movie, then again, you can recognize that this is Feynman. Of course, the beta was not bold. At this time, I don't know why. But anyway, I mean, this is really something that sometimes when I looked at this movie, I've seen, you know, pictures, old historic photos coming to life. And that's how they actually look like. And now, what I want to look you at this people who worked around Oppenheimer. A little bit later, I'll comment about the huge scale of the operation, which was $2 billion. But this was a nerve center of it because all the material which was made in different parts of the country came into this place as they need to make it work. So essentially, this center, a theoretical part, which Oppenheimer led it. This is Feynman, this is Klaus Fuchs, a spy, this is Hans Bethe. There were women there. And a little bit later, I'll comment of the origin of these people because it's also important. Here, I just want you to see historical pictures, and again, the same them looking, and here is the orange. So this is my personal interpretation. I did not read anything about it from there. So I think this recurring image of an orange, it is this orange. And it brings me as a physicist of understanding what was the problem. Because generally you may think, okay, so you have a small piece of uranium, there are some atoms, they divide, some neutrons go out. Well, this is a small piece, these neutrons just go away and don't do much. We have a big piece of uranium, these neutrons meet other atoms, they split them, they produce other neutrons, so it explodes. Okay, now how you make this big chunk of uranium? First of all, how would you know what is a big chunk of uranium that is needed, it's a critical mass to explode? Well, a little bit later I'll tell you how Germans estimated it and did it wrong, how British Rudy Piles did it almost right, but these people try to measure it, and when you try to measure it, you take two pieces of uranium and start slowly moving them together. The moment they approach each other and start contact, and this is a big enough chunk, the reaction starts over here. So what happens over here? It immediately overheats, it throws them away. This way they got a big doses of radiation. When they did this experiment, they more or less measured it, but they understood the problem. You want to get these pieces of uranium together fast, because the moment that they start getting together, the reaction started and explodes them out. And only small part of a very precious fissionable material would really react. So what you really need is to put around a usual explosion, which would make implosion, which would explode inside and compact this part and let it enough time to react so that the most of the material which is inside will react. The same problem on a much more complicated scale would appear in a thermonuclear explosion. So in a sense, this is something which explains, first of all, why this orange slices structure.
There are also atomic bombs that are called gun type. They actually use the
Yeah.
gun type in World War II.
You can do this. Yeah, you can shoot.
But they use gun type in the war.
Actually, there were also the first attempt to do thermonuclear was also gun type. It was called Zildovich pipe, and it never worked. But on the nuclear level, you can do this.
This is the plutonium one.
That was not uranium, it was plutonium.
That's plutonium, yeah.
The one that uses the implosion is not uranium. The gun type is uranium. The one that uses the
And the implosion type is plutonium, right? Okay, so, and this is a team which explains that the most complicated things, of course, were cross-section, was the probabilities of different things, it's really estimating. But then it was just a hydrodynamics of all this and geometry of all these things, particularly in thermonuclear weapon. And that essentially how the same person, von Neumann, participated in all this computation and also developed the first computer. Okay, so now just to give a scale, this is a scale. It's a order of the whole auto industry of United States at this time. So it's huge, right? And eventually it comes down to this small piece which need to really do it right and get most of this material which costed this much money to.
Never authorized by the Congress.
Yeah, this is a very American one. I don't know, maybe, yeah. Which means that this was all illegal. Yeah, there's many good things in life. Yeah. Okay. Anyway, so they did it. They exploded, and a little bit later I'll return back and I'll try to show you at least how I look at it and what I find amazing that they practically did no mistakes. And later I'll tell you how Germans did this mistake and that mistake, and they were actually, when they heard about what Germans did, they were ecstatic, they were laughing. But now I want to ask a very simple question. Was it a success or failure? So just to, no, in a purely historical date. They did it July 16, 1945. And the letter was sent in 1939. The work in a serious way started at 41, 42 actually. Reactor was built very fast. Again, maybe now I'll jump a little bit ahead. For reactor, which is a controllable nuclear reaction in which you do not explode, you really get the energy source of it. Is it something for which you need to slow down neutrons? And they were using graphite. And Germans were also initially using graphite, but it didn't work. It was expected to work, and it did not work. And there was a famous German experimentalist, Walter Botha, who measured the cross-sections in graphite. He said it would not work, and nobody ever tried and checked. And when Fermi and Szilard did it, they actually started in the basement in Columbia. There was a very private gift of money which allowed them to start it in the basement, and they started to work, and they understood that graphite does not work, but Szilard was a chemical engineer. He knew that there is graphite, and there is graphite, and there is other graphite. There are very different degrees of purity. And so eventually in America there was created an industry of producing very clean graphite without impurities, which allowed, when the money started to come on a government scale, to build very fast nuclear reactor. But bomb was made only in the summer of 1945. Again, there are very different perspectives on it. And there is the American perspective, which is mostly in the movie and which is Oppenheimer perspective. But here I just want you to see these people. First of all, this what we call Martians, namely people from Budapest. I also put here von Karman, even though he played a very different role creating American fighter planes. But here is von Neumann, Teller, thermonuclear weapon, and Szilard and Wigner. And those are people you see from all over the world. And of course, they were working like crazy between in 42, 43, 44, trying to make it as fast as possible to save Europe. And John Wheeler, who is not here, but who created a droplet theory of a nuclear with Niels Bohr, estimated the fact that they were late in 15 million lives. 15 million lives. Because they were aiming at summer 44. Again, there were kind of different things. If some of you remember the history of Second World War, the Budapest, Russians get into Budapest in the fall of 1944. Most of the Jews in Budapest were killed in the summer and in the early fall. And there were huge losses, of course, here and there. And there are many discussions if they would have it in the summer or fall of 44, where it would use them. Again, I am not privy, as it's still classified, the discussions about using it in Europe, but I believe they would use it on chemical industry, because when you look at where Americans and British spent most of their planes, I don't know, 500 or 600 planes were actually fell in one spot in Germany. That's where the farming industry stayed, which produced explosives and synthetic fuel. The moment they managed to bomb it in the winter of 1944-1945, the war was over eventually, because there were no fuel. Germany had no source of oil. They were using synthetic fuel for tanks, for cars. So they, from this viewpoint, from the viewpoint of Europe, they failed. And in particularly, I think it's, I don't remember actually exactly, Fermi or somebody said that from the moment, which was kind of late 44 until the summer of 45, they were really kind of very, very devastated. But Oppenheimer was really kind of, his role was particularly large during this period of winter and summer and spring, so that they finished the job by summer. When you watch a movie, somehow it's kind of, it's very concentrated. You don't see this big historical picture, but they were all people from all over the world, and they were all.
Can I make a remark?
Huh? Yes, sure, of course.
I think that from the point of Europe, they won a tremendous victory, because in 1945, there were 5 million Soviet Army people in Europe, and practically none from the West. And the reason why the Soviet Army did not move further than it did was mostly the fear, just the fear of the American atomic bomb.
But this was 45. Yes. I imagine they would be at 44. Of course, this was.
From the point of view of people who were building bombs, yes, it was perhaps it was a disappointment. From the point of view of Europe,
yeah, there was. You're right. There was positive historical side to it, of course. And now I want to look at it again from a European perspective and ask why Germans did not do it. Because these were people who were working hectic, and one of the reasons they really tried to do it fast, because they were absolutely sure that Germans would do it first. Because Germans were their teachers. You remember this first still with Oppenheimer and Rabi, it's in the train. The train goes to Göttingen. The two Americans went to Europe to learn fluid mechanics. quantum mechanics. They learn quantum mechanics, and that's all how it started. So here is a picture which I think tells it a lot of it, okay? So here are students and their advisor. Well, it's not easy to tell who is advisor if I cross. So here is the advisor. He's like 5 years older than his first student, Vic. Maybe, I don't know, Felix Bloch. No, Vic and Felix Bloch. Felix Bloch was probably first, Vic was second. The age difference is like 4 or 5 years. So this is Heisenberg. This is Plaschek. This person, that person, that person, that person, and that person, they're all people who built the bomb. This is Vic. It's very interesting. He is Italian, non-Jewish, which means that after Fermi left, Vic's theorem we use like every day, like. Yeah, sorry, yeah, it's just, yeah, this is Vic with W, yeah. So he was, after Fermi left, like the #1 Italian physicist, but he did not participate. Huh? I made a mistake? No, because I often do. And so he was not part of any project because German considered Italians unreliable, and all the rest went to America and did the bomb there. But here is a teacher, the greatest Heisenberg. And here I want to tell you something which some people know, but surprisingly many people don't, and I think it's very important. And it makes a historical background for this movie very, very. So in 1946, right after, actually the summer 1945, all leading German physicists were not arrested, but interned. They were taken from Germany to Great Britain, put into a small cottage which is called Farm Hall, and everything they said was recorded by eavesdropping devices. 50 years later, in 1996 or 1997, maybe I don't remember exactly, it was declassified. For young people here, I was tenure track, just trying to get my tenure, a very nervous time, doing some kind of passive scholarship. I dropped everything and spent like a few weeks reading this transcript. That was so unbelievably interesting. There are many interesting things there, because those are real conversation. And the people who were there, I mean, you can see this, just Heisenberg and Hahn, and who is the fission. So the conversation, what is given here is they had Times, and then they also had this BBC radio, and so they understand that Americans claim that they drop on Hiroshima a nuclear weapon. And they immediately start asking Heisenberg. So first of all, it's interesting that they always use term Americans. They understand that it's interesting. That's what why Pyrrhus was so proud that he did it and his teacher did not do it. But they don't. Well, maybe they did not know, so that their students did it essentially. But for them, it's Americans because it's a big country, it's a huge effort, etc. And then they start asking Heisenberg, well, but you told us that the bomb is impossible because the critical mass is so large that you just cannot put it on a plane. How you can put it on a plane? You could put it on a ship. And so that's why the Germans were actually trying to build reactor. And they did not build reactor either, right? So, and Heisenberg answers that, of course, it's impossible. This is just lie, because the critical mass is so large that it would not go off. Later, this is a common conversation in their dining room, but because there were recorders were everywhere, like half an hour later, Hahn and Heisenberg go into a separate private room, and Hahn asks, Hahn is very smart, it's clear. Well, they're all great people. He asks Heisenberg, how you estimated the critical mass? And Heisenberg starts to explain. And at this point, if you're a physicist, that's why I really wanted to give you a physicist perspective. It blows your mind away, because this is just childishly wrong, right? Well, I guess probably Pyrrhus said that Heisenberg was a great physicist, but not necessarily a good one. So he essentially estimates the mean free path. He asks, okay, here is a fission, uranium split, here is neutrons comes, but he can keep something else and produce some secondary neutron, or he can go away. So what is the size in which he won't go away? But of course, it's a wrong way to estimate. The right way to estimate is to ask, okay, there is a probability that it hits something, but it produces more neutrons that it actually absorbed over there. Next morning, he gave a right answer, which means that, of course, the moment he started, so of course he was a great scientist. He just probably, yeah, Volodya.
There was a belief that, which probably Heisenberg was the reason. He said on, I don't know where, that he actually specially
he made it intentionally.
The whole project to sabotage.
The beauty of wormhole transcript that you see how this beautiful lie appears, and it was not Heisenberg, it was von Weizsäcker who suggested, it was from the old German diplomatic family, nobility. And because we have records, so first of all, they are devastated. Then they ask Heisenberg, how the hell? Then Heisenberg gives the wrong answer. Next morning, he gives the right answer. And then they slowly start in this conversation. And they're all there. Just go. The book is in the library now. Start building this version that they were really human people, and they did not want to make a bomb. They wanted to make a reactor, which they failed either. Right? And Americans, they are really cruel people, so they will make you. Well, Americans also did the reactor and the bomb. So all this wormhole transcript put to death this beautiful version that they intentionally did sabotage. Because, when Heisenberg and Hahn speak in a closed room near the blackboard, and Heisenberg gives this bullshit about mean free path, then you understand that it's not, for external consumption. He just did a mistake. Okay? So I think it's really important to see that
who arrested him? Heisenberg.
Gauss-Smith.
Pash.
The same Pesh which is in the movie. This I did not know. Yeah, he was intelligence officer. But I guess Gauss-Smith was on the physics side in this. I don't forget how this mission. But it was probably called Olsos mission. Okay. Anyway, what is really this is a historical record. This book is now in the library. But I remember a moment when it just came. It was But another part of kind of summarizing is that Germans made these two critical errors, which nobody corrected. And at this point, you start appreciate not only the level of people and motivation who work here in America, but also the genius of Oppenheimer. Because it's really that this project, it's not a problem, it's a project. And there are many people, there are many directions. And when I think about it, and when I did few simple things, like practical things, related to people who were doing practical, there are so many dead ends, always. As practically they, did the right thing every time. Which means the fact that they were late, it was not their error. Of course, they considered it to be a huge misfortune, but it's just no way they could do it faster, because they avoided any error and any dead end. And great people on the other side did not do it. And maybe I'll just say a few words, and again, you're all welcome to comment. I don't find very interesting all this story about kangaroo court from the viewpoint of communist connection and all this. Definitely they knew everything about his communist connection before, and I think this is one of the reasons that Groves actually chose him, because he was kind of, in this way, more kind of controllable, etc. What I think, looking again, I'm not historian, but when I look at it as a physicist, the big shadow which allowed this kangaroo court to happen was thermonuclear weapon. So in a sense, in Washington, to let the hero, the most famous scientist in the world, to be put on this kangaroo court means that some people had some very serious doubt. Of course, Strauss was a bastard, and this was, again, was very kind of Jewish story. One Jew intensely dislike another for disrespecting him. I mean, go to any shtetl, you'll see such people. But it was allowed because I'm sure that there were very many people asking the same question. How the hell Oppenheimer tells us over and over, 1944, 45, 46, the thermonuclear weapon is impossible. Few years later, Russians do it. That was really, and at this point, you start understanding why Nolan in his movie put center and actually returns to it a conversation between Einstein and Oppenheimer. And that's what is the next part of the story. Why? What is the question that Oppenheimer asked Einstein? He asks him the question, which incidentally, he never asked this question Einstein. He asked Compton this question, historically. But I believe that this is a very right way for Nolan to make it like this. So he took this question about thermonuclear reaction and put it in between Einstein and Oppenheimer and made it a recurrent theme of the whole movie, kind of and then it's also in the end. And which is kind of, it's not a historical truth, but it's kind of higher level of, I believe. So what is this question? And the question is what physicists call a Fermi question. Again, coming back to Rabi and what his mother told him, did you ask a good question? That's what science is about. Science is about asking questions. And Fermi was probably, I think, that like world champion in this sport. And he asked questions like how many times you need to lick an ice cream to finish it. And the questions was meant that before you took ice cream, you look at it and you say how many times. This is the way I also train my students. Yeah? Like do estimates. Try to do estimates, order of magnitude, 2 orders of magnitude. Or I don't know, what other Fermi questions here? How to estimate power of explosion using a sheet of paper. Fermi answer. Take a sheet of paper, drop it into small pieces, put a pile of it. There is explosion somewhere. You look how they are scattered. 30 seconds, he gives the answer. They were actually competing with Feynman, who does this better. So Fermi asks this question. If we make a nuclear explosion, could it be that in the atmosphere a chain thermonuclear explosion starts? That was Fermi question. It was asked. Of course, we're talking about nitrogen, because the atmosphere is mostly nitrogen, and so it was essentially the question, could it be that instead of splitting one big uranium nuclear, this is nuclear, fission bomb explosion, we take somewhere overheated 2 nitrogen nuclei which hit each other and create a compound nuclear and release much more energy, which would hit another nitrogen atom, nuclear, etc. So this is the question which historically, when Fermi asked this question, Oppenheimer went to Compton and they discussed it and did not get much. And then Bethe, of course, Bethe computed everything. Bethe did the first estimates. So this is the question. And now to answer this question, you really need to know what we call cross sections. The probability that 2 nuclei not just fly past each other, but can really interact strongly, create a compound nuclear. It's like a drop. That's what Wheeler and Bohr created for us, this droplet series. This is just a drop, and it would kind of oscillate, and it could break, or it could just relax and stay this way. Okay? So a way to compute it goes back to the work of Russian George Gamow, who was the first to apply quantum mechanics to nuclear. And as that I've heard, alpha decay. The first thing he did was alpha decay. Yeah. And Rumer told me this story. They were all coming to Göttingen to learn quantum mechanics, and Gamow came later in the day. There were no one around, and there was this very German organization of this famous place, Göttingen, where Max Born was a professor. So everyone was given a key. So the key of a student opens his door and library. This is the first question. The key of a more senior student opened his door, the library, and a room where 5 or 6 students sits. And of course, professor's key opened all the doors. So Gamma was given a key, and there was nobody around because it was already close to evening. He went to the library, read some paper, and by the morning he has, it was 1927, 28, I don't remember exactly. By the morning he had a nuclear alpha decay theory on the barrier, etc. And then of course Taylor, they were very good friends.
Taking one integral, which he asked his friend.
Really?
The famous integral, give gamma factor. He couldn't do. He asked some friend mathematician who
Yeah.
did.
Yeah. Incidentally, I think that this is the most underappreciated physicist of 20th century. I think that he probably deserved 2 Nobel Prizes, maybe even 3, if you take also triplet code in biology. But anyway, so these are the people who were doing this computation and developing them into really quantitative science. And of course, it's all was very, very speculative until 1961, when Russians exploded what is called Tsar bomb, was really huge, and then we can really measure what percentages of different elements. So this is all about probabilities of hitting here and there, and those are the people who did it. And after Fermi asked this question, this guy was totally obsessed with this question. And it is in the movie, it is this scene which shows Taylor. Well, of course, Taylor was prima donna, and the moment that Bethe was made a head of theoretical department, he was kind of really did not want to be a second fiddle. And this is a scene in the movie when he tries to leave, and Oppenheimer tells him, "Okay, stay, do what you want." And from this moment, you see this K6, what I show you, this K6 group, which was the center of the project. Taylor is a fantastic personality, and I can spend like 10 hours talking non-stop about him. It's every one of these people except Oppenheimer left a big trail on YouTube. If you go to YouTube, you find Wheeler, you find Taylor 12 hours of memoirs, really very interesting. Telling, well, non-classified stuff. So from this point, Taylor really was working and thinking about thermonuclear weapon, and everybody else was working on nuclear weapon. I don't think they missed him because they were really great people and they were doing everything right, but Oppenheimer was all the time very much against it. He did not like this work. He did not think that they need to do it. He actually retained Taylor for a very long time, but the relations were very strained all the time. But if you look at, here's the first actually text is Taylor-Konopinski, again, classified report. So what we see, what physicists see when we talk about nuclear and thermonuclear, or fission and fusion, we see this curve. But this is the only piece of kind of physics that I want you to see, because it's relatively simple. It's how much energy is per nuclear. You see, here at the top is ferro.
The opposite side.
Yeah, we would put it like this, but this, nuclear engineers always plot it like this. So this is the most stable iron. Iron is the most stable element. It is on top, right? Here are light elements. Here are heavy elements. So when you take uranium, which is over here, and it splits, you get from here to here. This is your fission. It's a very, very, not a very steep curve. So you get that amount of energy out of nuclear weapon. When you take light elements, tritium, lithium, beryllium, and you fuse them together, you jump from here to here. This is your thermonuclear weapon. Okay? So that essentially, when Fermi was asking his question, he was seeing this very asymmetric curve.
Jumping from this.
Well, if you really can, but look, well, first of all, I mean, Vitaly, no, but look, I mean, it's, yes. Look, this person, which fortunately later got his Nobel Prize, Vitaly Lavrovich Ginzburg, actually kind of made his point on this huge minimum. This lithium is a very important part of thermonuclear. Huh? Yeah, okay, but here are some Russians, declassified Russians in the room. So this is really something that you want to understand very, very quantitatively. So essentially, what we really talk about, thermonuclear, nuclear, this is this curve. And this is pretty smooth, but this is pretty sharp. And there are huge differences between very, very close elements. This is just Li-6. This is tritium-3. This is a very small differences in the nuclear mass, but it's a huge difference when you fuse this together. Okay? So this is also what I want you to see when we talk about it. And those now Russians come into story. Again, if you really now start to see it from the perspective of Einstein, Oppenheimer conversation, you understand that it's about thermonuclear weapon. And I'm now talking about thermonuclear bomb. Russians got their nuclear bomb by getting classified data from Fuchs and other spies. It was interesting modus operandi how they did it. Again, a lot of things that I'm telling you, I've heard from people who heard from people, and some people actually was there. So this one thing which I learned from Levitch, who is the son of a guy who was a secretary of Kurchatov, and Kurchatov got this Hume, what we call Hume-int information from Klaus Fuchs spy, and then he was given, like Oppenheimer, was given problems to different people whom to solve. Kurchatov was given problems on nuclear weapon to different scientists, and they did not know the solution. He knew approximate direction. They were all absolutely sure that Kurchatov was a genius. They did not know about spy data. But Oppenheimer was a genius because he did it first, right? But now we're talking a second stage where real geniuses came, Russian geniuses in this case, and here's American geniuses. And now what you see here, John von Neumann near his first computer, which was done a little bit later because when they were working, and there's Steller and then Stan Ulam, who is another guy from Chernovtsi, I guess, that region. Where are you from, right? That's where Zohar is from. Stan Ulam came 2 generations before Zohar from this region. That's Sakharov, Zildovich, and Ginsburg. So they were the people who created the most energetic event in the history of mankind, thermonuclear explosion. And this was done independently by Russians and independently by Americans. The first idea that Sakharov invented, he was 27 at this time. I believe that he was really great scientist. And it's, for me, it's kind of a personal loss that he spent most of his life doing all this weapon classified work. He was very close. He started to do quantum electrodynamics in a very right direction. But then went to do all this stuff. But why it's important and why it's a computer here, that again, the way that all this work was like this. You really want these light atoms to hit each other. And of course, there is a barrier because this nuclear here, they're all positively charged. This nuclear here is also positively charged. They don't want to approach each other. So you need to hit it very much. They need to fly at a very high speed. The moment they fly with a high speed, they can also fly away with a very high speed. So you want to, as they say, hit and hold or compress. And one of the ways to do it is that you create a nuclear weapon over here. Now, like a usual explosion could create implosion and produce nuclear weapon can create implosion and produce a thermonuclear explosion. So in a sense, what Fermi asked now needed a lot of computations. And the equation of state was unknown. And the whole, if you look at, you think about implosion, you immediately understand that it's very unstable. It does not want to remain spherical. The moment it's like this, it immediately starts compressing in this direction and expanding in this, and you lose it all. So you need to keep it from developing all these instabilities over there. And it's a very complicated geometry of it. And it's needed a lot of computation. And that's why the first computer and the first thermonuclear weapon, they, in a sense, came from the same people. And were doing kind of, and of course, von Neumann was not motivated only by practical things. And if you really look at the history now of informational age, not energy, then you realize that Turing and Shannon, they were, in a sense, the people who were inspired by him, who not formally his students, but they were kind of younger people whom he taught, and he actually very much wanted to have Turing at Princeton. And this is a separate story. But what I really want you to see is that the real problem that they were doing, and the central thing in the movie, which kind of understood, if you understand what Einstein was talking to, is a thermonuclear problem, and this is something which is closely related to this very heavy computational problem. And so eventually they did it, and this is Ginsburg LID. Now, only maybe one last comment, because I'm already speaking for 50 couple of minutes, is a very curious analogy, and this is very personal for me, between Oppenheimer on American side and Landau on the Russian side. Landau was a theoretical physicist with a little bit younger. Oppenheimer is 1904 was born, and Landau was born 1908. They both had this feeling which Landau formulated like all pretty girls are married, all great problems are solved. Our generation has nothing to do. And they did very similar, played very similar role in their respective country, namely they returned and created a school. In the movie, it's a very nice sentence which Oppenheimer says, why would you need all these foreigners if we have our great school of quantum physics in Berkeley? But I say, yes, I created it. And of course, the same way also Landau created it in Russia and also wrote this course for the whole. But it's one interesting analogy which is very little known. I actually never read it somewhere. I know, but I know it personally from people whom I trust 100%, is that they were both very much against thermonuclear work. And I've heard this from Zildovich, who was saying that Landau actually shouted at him and called him bitch, which is not a swear term, it's a terminology, which if you are in prison, it means that there is some prisoner who is now on the side of guards. Which for Landau was people who were doing thermonuclear weapon for Stalin. And Sakharov also describes in his memoir very interesting. Sakharov was 27, really young guy. And Landau was, you know, a teacher of his teacher and of all of them. And Landau took him out of the building, which was very unusual, and started to tell him that maybe not a good idea to go into these classified places, etc. And Sakharov, much older person who writes this memoir, clearly that he did not understand what Landau was saying. He understood it only much, much later. It's also another interesting analogy that they were both kind of tried, and well, Landau was jailed, but he was jailed for a real thing. He really wrote anti-Stalin leaflet, which was another curious ricochet in all this. When Oppenheimer was arguing with Teller whether it's a need, a military political need of doing thermonuclear weapon, he says that we are allies with Russians. We're fighting the same Nazis. Then we probably can, after the war, agree with each other. And Teller told him, no, there is no way to come to any agreement and to trust Stalin. And it was very personal. Everything was personal for this. And then Teller asked him why. Oppenheimer asked why, and other people. They were actually, and Teller say, I remember Landau. When Landau came to Göttingen, he was totally communist by his ideology. If by 1937 Landau came to the conclusion that Stalin is a criminal, then Stalin is a criminal. Then you cannot trust him. It's very interesting how this personal fact that they were all in the same Göttingen, and then in Leipzig with Geiselberg, and in Berlin they all come in for seminars, and they knew each other personally, that Teller so much trusted his gut feelings about Landau, and Landau got feeling about it. He says that America needs to have thermonuclear weapon, otherwise there could be a big nuclear war with Stalin. So it is on this kind of maybe little known piece that I maybe wanna finish, or maybe just one last thing of energy. That the same person, Sakharov, the same year, invented probably the way in which 200 years from now mankind will get its energy, and it's a controlled thermonuclear reaction. Huh?
Why 200?
Because not like you, I started in a plasma group. And when I started in a plasma group, and it was 45 years ago, everybody was saying that in 10 years we'll have working tokamak. So I have my pessimism, you know, paid by 40 years of my experience. But it's really a short piece of really curious history. So everybody was thinking about thermonuclear reaction as something that you implode in and create something very dense. Because they're a really small nuclei, and you really want to compress and have a big density. And then in 1914, where are the dates here? Probably in 49 or 50, the guy, by the name Lavrentiev, he was a sergeant in the army, doing radio, technically kind of high school educated person, wrote a letter to the Central Committee of the Communist Party saying that you really need to do a controlled thermonuclear reaction. He was reading popular books in physics. Apparently a very smart guy. He later got his PhD and worked in Kharkov. And so you need to do a controlled reaction. And for this, you need to heat, but not compress. Which means you need to work with the gas of these light atoms, just keep them long enough so that it will be going over and over and over, and then hitting each other from time to time. And from Central Committee of the Communist Party, they gave it to the scientific advisor of Sakharov. And of course, he gave it to his PhD student, Sakharov, this project. And Sakharov wrote, here is this reply, explain why it would not work. That this configuration of he suggested electric field, and it was totally unstable configuration. But Sakharov continued thinking about it, and he invented toroidal configuration of a magnetic field, and tokamak is now working. So you're right, I mean, it's working, it just eats almost as much energy as it produces. So maybe not 200 years, maybe 20 or 30 years it starts to be, but it's unlimited source of energy. So eventually this thermonuclear reaction is our unlimited source of energy, and of course that what gives sun its energy. So this is the story, this way comes a full circle from one form of energy to another. And at this point, I want to finish my story, and you're welcome to comment.
Does anyone have any comments or thoughts that you'd like to share?
Objections, comments?
Disagreements?
No, I just want to say thank you. I am not a scientist, and so I really appreciate the opportunity to hear this history explained.
A bit of science makes this drama even more dramatic, right? Exactly, exactly, yeah. Mm-hmm.
Anyone else?
Oh, I actually have. So you said that Heisenberg actually wanted to create.
I don't know. I don't know what he wanted or not. He made a simple error in estimating critical mass.
Maybe his heart wasn't in it when he was trying, but maybe not very hard.
I really, first of all, I respect him enormously, right? He's a great scientist. And he actually was a very good human being, from what I know. So maybe his heart was not there. But generally, if you're a scientist, you don't just do something. You check it like 5,000 times, right? And then you, so he did not. Yeah, Volodya.
Story about heavy water. That was the first. Тяжелая вода.
Yeah, heavy water.
Heavy water. It was the first line of their research.
Yeah. Yeah. Yeah, I did not tell this part because this is the part which was right. Germans did write many things. This was another source of slowing neutrons, heavy water. Yeah, but this I did not comment, and I don't.
They abandoned it at the end.
No, they did.
I know they were actually working. I mean, and they were. I mean, there was absolutely hectic work in May '45. They were relocating their nuclear reactor in project. They were sure that in few weeks it would start working. You know, it was a, you know, a race. Yeah.
Any last thoughts, comments? Thank you very much for sharing this.
Thank you.